Hello everybody, here's a narrated PowerPoint for Chapter 5. As a brief introduction, we're going to talk about z-scores today, including what they are, how to calculate z-scores from raw scores, and how to calculate raw scores from z-scores. And then we're going to talk about ways of comparing z-scores from different distributions and why it is important to do so. First, let's put today's lecture into context. We've been looking at these raw scores in previous classes. These show 200 IQ scores of FSU psychology majors. The point we've been making is that we can learn a lot about FSU psychology majors by looking at these intelligence scores. However, it's very difficult to make sense out of that. So what we've been talking about in this section of the course is descriptive statistics, ways of describing or summarizing data from a sample. In Chapter 2, we talked about how we could make frequency distributions from raw scores in either graph form or table form to show the frequencies of the different raw scores. So yes, it is much easier to understand the raw data when we look at them in graph form or table form like this, but it still takes a lot of effort to produce those graphs and tables. What we saw in chapters 3 and 4 is how we could summarize a set of scores with two values: a measure of central tendency of the middle or average value in the distribution, in this case the mean, and a measure of variability showing how spread out the scores in the distribution are. So what we're going to talk about today is how we can describe individual raw scores in a data set. And we're going to do that by looking at z-scores. So z-scores tell you the relative standing of a raw score. That is how that raw score compares to other scores in the distribution in standardized units. Let's go through an example. The example data we're going to be looking at today are these attractiveness scores. So what we might do is to take pictures of 100 different men and have women sit down and rate how attractive they find the different men to be. At the upper part of the distribution, we might have scores for very attractive men like Harry Styles. And at the left side of the distribution, we have the attractiveness scores for men who are, maybe not as attractive, like poor old Larry King down here. Now, we can see that we have three people highlighted in this distribution: Chuck, Sean, and Brandon. If we look at their individual raw scores, we can see that Brandon's raw score of 90 is pretty high, right? His is towards the upper end of the distribution, showing that he's a pretty attractive fellow. Sean is towards the middle of the distribution, maybe slightly above average. So yeah, he's slightly above average in terms of his intelligence. And then poor Chuck is way down on the left side of the distribution. Chuck just isn't a good-looking fellow. Now, we can see that we've been able to verbally describe the basic relative standing of Brandon, Sean, and Chuck. Brandon is a pretty attractive guy towards the upper end of the distribution. Sean is an average-looking guy, maybe slightly above average, whereas Chuck is not very good-looking and has a lower raw score compared to the other scores in the distribution. But that took a long time to describe the relative standing of those three guys. Wouldn't it be nice if we could describe in standardized units in quantitative fashion exactly how a particular raw score compares to the other scores in the distribution? Well, that's exactly what z-scores are going to be able to tell us. So the z-score is the number of standard deviations a score is above or below a sample or population mean. I really like this sentence because it shows just how far we've come in this course. That is, if I gave you this definition on the first day of class, you guys would have no idea what this sentence means. But now we know what standard deviations are. They are the average amount that scores in the distribution differ from the mean. We know what populations and samples are, and we know what the mean is. So a raw score's z-score is simply going to be the number of standard deviations it is above or below the mean of the distribution. For instance, we looked at this graph last week when we were looking at the percent of scores that fall between the mean and various standard deviations in a normal distribution. And we saw, for example, that we could have scores that were, for example, 1 standard deviation above the mean, or 2 standard deviations below the mean, or a score that is 3 standard deviations above the mean. And we're pretty comfortable with that, right? We basically understood what that meant for the score to be above or below the mean by a given number of standard deviations. So the point here is that when we talk about a z-score, what we are describing is the number of standard deviations that score is above or below the mean. So for example, if we say that a particular raw score has a z-score of 1, well, that's just saying that z-score is equal to 1 standard deviation above the mean. A z-score of -2 would be 2 standard deviations below the mean, or a z-score of 3 would be 3 standard deviations above the mean. If we were to go with non-whole numbers, we could sort of get the exact same sense. So let's say we had a I had a z-score of 1.5, which would fall right around here. Well, all that is then is the number of standard deviations that score is above or below the mean. So again, a z-score of 1.5 would be 1.5 standard deviations above the mean. It would fall right around here. We should also be getting a sense of how the z-scores correspond to how close or far they are from the mean. We can see, for instance, that a z-score of 3 is pretty far above the mean, right? Whereas a z-score of -1 is sort of slightly below the mean. A z-score of -1.5, for example, would be slightly below the mean. Again, right around here. So again, when we're talking about z-scores today, we're talking about the number of standard deviations that score is above or below a mean. Let's get a little bit more technical now. We're clear about what we are referring to then when we talk about the z-score of a particular raw score. So there are two things about a raw score that the z-score will tell us. First of all, whether the z-score is positive or negative tells us whether the score is above or below the mean. So quite simply, if the z-score is positive, or if you don't see a sign in front of you can assume it's positive, that means the z-score is going to be above the mean. If the z-score has a negative sign next to it, that means that particular raw score will be below the mean. Then the absolute value of the z-score is going to tell you how far it is from the mean. The larger the z-score, the farther it is going to be from the mean. For those of you who don't know, the absolute value of the score is basically the score ignoring any signs in front of it. So you don't pay attention to whether it's positive or negative, you just look to see how big the number is. And yeah, the bigger the number, the farther that score would be from the mean. So just to summarize this together then, a large positive z-score would be far above the mean. I would say any z-score that's larger than like +2 would be considered a large positive z-score. And it would be, again, far above the mean. A small positive z-score then would be a score that's slightly above the mean. Yeah, so anything from 0.1 to about 2 would be what I would consider to be a small positive z-score. It would fall slightly above the mean. A large negative z-score would be a score that's far below the mean. Again, anything that's less than -2, so like -2.5, -3, -4, those would be large negative z-scores that are far below the mean of the distribution. And then a small negative z-score would be a z-score slightly below the mean. Again, generally speaking, anything from like -0.1 to -2 would be scores that are slightly below the mean. Let's use what we just talked about to go through some examples. So in each of these examples, I'm going to show you 2 z-scores, and you have to decide which of those z-scores is farthest from the mean of their distribution. And remember, to do this, you're going to look at the absolute value of the scores. You're going to look at which number is bigger, ignoring any negative signs. Okay, so which of these numbers has the biggest absolute value, which is the bigger number, 2.45 or 1.76? Well, 2.45 is bigger than 1.76, so that would be the z-score that is farthest from the mean of its distribution. What about these two, -0.79 or -2.44? Which of these is going to be farthest from the mean of their distribution? Well, again, take the absolute value, ignore any negative signs. If we ignore the signs, 2.44 is bigger than 0.79. So what that means is that a z-score of -2.44 would be farther from the mean of their distribution than a z-score of -0.79. And then finally, -1.76 versus 1.12. Again, take the absolute value, ignore any negative signs. 1.76 is bigger than 1.12. So what this means is that -1.76 would be farther from the mean of its distribution than 1.12. And then which of the above z-scores are below the mean of their distributions? Excuse me, which of the above z-scores are below the mean of their distributions? To answer this question, we just want to see which of these z-scores over here, up top here, are negative. So to answer that question, we just look through for any negative values, and we can see that it would be the ones with these negative signs. So negative 0.79, negative 2.44, negative 1.76 would be the z-scores that are below the mean of their distributions. Now, I had an absolutely horrible time today putting these YouTube videos together. I don't know why. So unfortunately, I had to break it up into 2 videos. This is going to be the end of this video, but then click on the other link in Canvas to take you to the next video. And the exact minute you should go to in the next video is mentioned in Canvas. Any questions, just send me an email.